together, and I'll end up with the CPC. This is the two-dimensional CPC. So again, what has happened here? I've taken so this is the full parabola we were just looking at. Okay, it's just rotated. And the axis of that parabola is shown here. Okay, this is exactly the same, just rotated a little bit counterclockwise. Now, keep in mind, we had a ray of light coming in like that, and we saw that that focused onto the focus here. That was the focus of the parabola. Okay, all of that is fine. Any parallel ray comes in here, it ends up at the focus, right? I can do that. Any parallel ray coming in here ends up at the focus. So that's exactly what we just saw in the previous slide. I'm going to erase that. Now I'm going to reflect it off about this axis here, the vertical axis, and form another parabola here. Okay, that does the opposite, right? So now I have a ray coming in from this direction. It will reflect and go to this point here. I can have parallel rays coming in here, goes to this point here. Another ray coming in here, goes to this point here. All of them go to this focus. That's the focus of the second parabola. Okay. Now, of course, I have truncated the parabola, both the parabolae, right? I've truncated it at the focus at these points here. And that's because I want to put them together. Otherwise, they will intersect. And I want to put a receiver here, right? So I need some room. So I've removed this part that's dashed. So I've truncated the parabola and put them facing each other in a symmetric fashion. Okay. So now, if I were to just look at the solid lines, which I'm shading, what is this doing? This is now taking any beam of light. I'm going to draw it with a different color. I can take any ray of light. This is my edge ray. This gets focused to this point. And I can draw another edge ray, the same angle. Let's call that theta. And we'll define what theta is shortly. It will go to the other edge, right? And if I say this is my solar cell, I've captured those edge rays. Now, by definition, I know that if I come in at a different angle, smaller angle, I will end up somewhere in between the edges of the receiver. I don't know exactly where they will go. It's not an imaging element, but it will go. I mean, I know exactly where it will go, but it's not an imaging element. So I shouldn't say it that way. It will end up somewhere in between. So again, keep in mind the design we did was to ensure that the rays at the edges, the largest angle ends up at the edges of the receiver. And if I come in at a smaller angle, anywhere in between, right? These are all smaller angles, even straight, that's zero angle, I will end up in between these 2 points. And that's exactly what I want. I want to collect, if I were to think about on the input side, what am I seeing? I have an input aperture here. I'm seeing a bunch of rays, right? I have a bunch of rays coming in at all kinds of angles. I want to collect all of these as much as possible. In this case, I have a certain collection angle of theta in this direction and theta in that direction. Beyond that, of course, I don't collect it, as we will see, as we saw before, and we will see again. Okay. Now we will review it. So it's good to kind of visualize this so you understand what the light is doing. Now, you might ask the question, what happens if I keep extending the parabola upwards? And you can say, oh, why can't I keep going, right? Why can't I keep making that entrance aperture larger? Of course, it's common sense that at some point it will start bending in, because again, this parabola is going to bend in, right? I mean, this is a parabola. So the shape will continue going the same direction. The equations are exactly the same. But at some point, it will bend inwards relative to this axis here. So that means it will start shadowing the light. So now you'll start losing power. So another way to think about it is that if I put two of them, there is an optimum height of this CPC such that my CD is largest. My entrance aperture is largest. This is my entrance, and that's my exit. I can keep increasing it upwards, but my C4D4 is smaller than CD. And then what that means is, of course, that it is going to block some of the light from coming in, as you can see in this picture. Okay, I think so far it should be relatively straightforward. Now, let's review this whole concept of edge ray principle that I've been talking about for the last 10, 15 minutes. Light rays coming from the edges of the source must be reflected onto the edges of the receiver. So again, the edges of the source to the edges of the receiver. And if I design something such that edges of the rays from the edges of the source reach the edges of the receiver, then I know that all the rays in between will actually receive some point on the receiver. And this is the basic design principle of non-emitting concentrators, something called the edge ray principle. So when you're trying to design something, you essentially look at the edges of where you want to collect the light, and that edge can be a spatial edge, like the size of a lamp. It can be an angular edge, the angular extent of the sun, for instance, right? It can be something in between as well, like in an automobile headlight. What is the rays that are coming out? It's coming out from some LED light source. Then what optical system can you put in the path of these rays so as to achieve a certain output? In the case of the CPC, all the rays entering the CPC with an input angle less than theta, which we defined, are trapped and end up at the receiver, which is what we want. But all the rays entering the CPC with an angle greater than theta are lost, are reflected back. And that's demonstrated in this picture here. So here again, the edge ray has an angle theta, will end up at the edge of the receiver. So that's well and good. Now I'm coming in at an angle theta1, which is less than theta. That's also good because it just goes to 1 point on the receiver. I'm still collecting it. I haven't lost it. But here's a situation. I'm coming at an angle theta2, which is larger than theta. Of course, that means that it'll again obey the law of reflection. In this example, it's hitting the other side. And then, although I didn't draw this perfectly, it will simply escape the system. In fact, you can show this generally to be true. I mean, this is a very simple example that I drew here. So if I can define something called an acceptance of the CPC, this is simply the number of rays reaching the receiver or accepted by the receiver divided by the total number of rays entering the CPC. Now rays is simply a stand-in for power or power density, right? Because in geometrical optics, if I count the rays as the same as is a measure, it's proportional to the power density of the light. So it's also an efficiency metric, this acceptance. In an ideal CPC, which we saw in the two-dimensional, two parabolic CPC, is an ideal CPC that has an acceptance angle that is 100% for 100% acceptance until it reaches the edge angle theta, acceptance angle, half angle theta, and beyond that it goes to 0%. So in other words, all the angles less than the designed acceptance angle is 100% accepted. Anything beyond that, nothing is accepted. Now, in reality, of course, it's never perfect like that, as we will see later on. Now, I can think about this, the geometry of the CPC from the perspective of Fermat's law as well. So again, it's just a different way to think about it. I should speed up a little bit, sorry. Is again, for a general parabola, we know that if I take these two lines, AC, plus CF should be equal to BD plus DF, which is shown here, right? This we know from this locus of the parabola. So we can write that equation in the context of the CPC at the bottom here, where CB, which is, let's see, where is CB? Is this distance, plus A2, which is the length of the receiver. So I'm only looking at one side of the receiver. That's that, is equal to E to D plus dA. Okay, as shown here. This just comes from the fact that this is a parabola, right? Those path lengths that we see, you just rotate it, it's exactly the same as this. Now, we also know that CB equals DA. So what's CB? CB is this line, is equal to DA just from symmetry. That's just isosceles triangle, two isosceles triangles, but it's just also from symmetry. So we can cancel these things out. So I get a very simple expression, A2 equals ED, which is nothing but A1 sine theta. What is A1? A1 is this, except entrance aperture. Sine of theta is this, A1 sine theta. So now I have a very simple expression, A1 over A2 is 1 over sine theta. Now what's A1 over A2? This is nothing but the concentration factor, right? In 2 dimensions. So it's simply the area of the entrance aperture, or the size of the entrance aperture divided by the size of the exit aperture. So I have a very simple expression that the concentration factor is inversely proportional to sine of the acceptance angle. Okay, and this is very, very fundamental point. This is actually related to the second law of thermodynamics, as we will see shortly. Now, I can use these relationships to figure out the geometry of the CPC. So what else do I need to know? If I know the receiver size is A2, the entrance size is A1, I need to also know how high the CPC is. Oops. Okay, we have a visitor, but let's continue. Hi, Anne. We need a few more minutes. Welcome. Let's continue. So if I give you the size of the receiver, which is shown in A2, and the size of the entrance aperture, which is shown in A1, I can figure out the height of the CPC from simple geometry. Again, it's quite simple. I can simply draw the edge rays as shown here. These are the edge rays, and then I'm just dropping a perpendicular. And I can say, okay, my total height, H is H1 plus H2. So I have H1 here, I have H2 here. And H1 is simply A1 divided by 2 divided by tan theta because of this triangle, right? This base is A1 over 2, this is H1, and tan theta is simply A1 over 2 over H1. So you guys are very familiar with this. I can do the same analysis on this triangle here, whereas this base is A2 over 2, and I get these two terms over here. And I can simplify it like that. So now, given an A1 and given an A2, I can compute also the geometry, the rest of the geometry of the parabola as well. Now, there are a few things to keep in mind here as we try to gain intuition. One is as the acceptance angle increases, right? Now, by the way, what does that mean by acceptance angle increasing? That means I can now collect a larger cone of angles. Now, from a practical purpose, this is actually quite nice, right? Because that means I don't need to track the sun so much if I can collect a larger cone of angles. So what is that? And so that's a very desirable property. But we know from the previous slide that if I increase let me go back from this previous slide, if I increase my theta, so increasing theta is a very good thing because I want to collect more of the angular extent, so I don't need to track the sun, for instance. However, if I increase the theta, I'm going to decrease my concentration factor, so I cannot concentrate it as much. So you can now get an inkling of why this is very fundamental. It's actually limited by the second law of thermodynamics, so it's nothing you can do to get around it. Although there are a few caveats to that point, which I will come back to later on. Now, of course, increasing theta from this equation means that you're increasing the total height of the CPC. In other words, the CPC is getting huge. So that's also quite problematic, right? As theta goes to, wait, let me see. Did I make a mistake? Yeah, I probably did. So this, as theta goes to 0, H goes to, actually, as theta decreases, H goes to infinity, right? So the narrower the field of view that I have of the CPC, it gets really, really big. Of course, if I expand the acceptance angle, it gets really stubby. right? But of course, that means that my concentration factor is going down. Again, let me just draw what I just said. So I can have a situation where I have very, very, very big, with lots and lots of concentration, right? So in other words, I have a very small receiver here, big aperture here, or I can have a very, very small aperture here and a small aperture here. So I can have very short CPC or very long CPC. The big difference is that the theta here is small, very small theta. Theta here is large. But concentration here is small. Concentration here is, concentration here is small. As the ratio here is large. Okay, I think you all understand what I mean. I want to talk about two more things, and then have Anne talk a little bit about what she came to talk about. Now, as I said, so far we have seen that the CPC is an ideal concentrator in 2 dimensions. However, our universe is, of course, not 2-dimensional. Our universe is 3-dimensional, so we have to live with the fact that the CPC is actually not ideal in the real world. And there are many ways you can adapt the 2-dimensional CPC into 3 dimensions. Now, I'm going to show you just 2 examples of very simple things. Now, simple ways to do it. There are many more complex ways to do this. One is you can do this as a separate 2 separable Cartesian functions. So you can have an XY CPC and in the other axis you can have a YZ CPC, and you multiply them together. So essentially 2 separable functions. Another way to say it is that you have an X CPC multiplied by an FY CPC to define the XY. And H is, of course, the height. The other way is, of course, to make a rho a rotationally symmetric. So you take a CPC and rotate it about the axis, which is the simple way most people do it, as you saw in the video at the beginning. Now, of course, in either case, it can be shown that some of the skew angles, which skew angles mean angles that are not coming at in a plane that is defined by the axis of the CPC. So it's outside this kind of a definition of the plane. You can show that these skew angles will actually escape. And you can show this with some 3-dimensional ray tracing, which we won't get into at this for the purpose of this class. So I'm going to show one more thing here. So we saw the acceptance criteria for the CPC in 2D had a very nice property, right? It was 100% below the acceptance angle and 0% above certain acceptance. What happens in 3 dimensions is a bit more nuanced. You essentially get a plot which goes like that. So you might have a theta, but it's not 100%. So you get this smooth happening, smooth loss of power here. These are due to the skew rays. Something to keep in mind. Okay, very good. And